Okay, AP Statistics. In this video, we are continuing through our Unit 2 notes, and we are continuing in 3.2 in the book. That's section 3.2 in the notes and in the book. So in this video, we're going to talk about how we determine if a linear model is appropriate, and then we're just going to kind of finish up the notes here. So determining if a linear model is appropriate. Keep in mind that just because we have an explanatory variable and a response variable and they have a relationship doesn't necessarily mean that a linear model is appropriate. For instance, let's say I have a scatter plot that looks like this. Well, let's say if I collected more data and it started looking a little like that. Well, that's going to make a curve in my data. So if I'm looking at a finite number of ordered pairs in a particular set of data and it looks linear, it may not be continuing that trend should I gather more data as X increases. So because I'm looking at a finite set of points and I can't see where it may be headed should I gather more data, I can't naturally assume that just because it looks linear, a linear model is the best fit for the entire set of data. So the residual plot helps me determine that. Your residual plot is essentially a scatter plot that shows you your residuals based on a situation like this, okay? So it places it on a vertical axis, so it changes your y values to the residuals, and the explanatory variable, of course, stays on the x-axis just like it normally does. So it basically takes that line of best fit, or that LSRL, and kind of straightens it out so that you can see your residuals perpendicular to the x-axis rather than at an angle on the LSRL. And when I say LSRL, I mean least squares regression line. Okay, so when we think about the residual plot, you need to understand that when we look at the residual plot, it is either going to indicate to us that the data's a linear model is a good fit for the data, or a linear model is not a good fit for the data. And what we want to see in a residual plot, we want to see a nice scattering of points. In other words, I want to see something that looks like this. I don't want to see any kind of pattern. All right, I just want to see a scattering of points. And you may be asking, well, why does that matter? Well, if you'll think about how we come about a residual, we take the actual y value and we subtract the predicted y from it. So you need to think of it this way. Let's think of the form of our residual. So the form of the residual, and by that I mean whatever the scatter plot of the residuals looks like. So the form of the residual would equal my actual y, and I'm going to call this the form of my association because that's the form of your original scatter plot, minus y hat, which is your predicted y value. So that's going to represent the form of our linear model. Okay, so I'm going to call that form of the model. Well, we're not going to have any perfect data, so these values here are never going to equal 0 unless an ordered pair lies on the line of best fit or the prediction line. But in theory, if the form of the association minus the form of the model, if these are the same, then the form of the residual will equal 0, meaning that we have a random scattering of ordered pairs in our residual and no form. So the form would equal 0. So if the form of the model's a good fit for the association, when we subtract those, we should theoretically get a 0, meaning no form in the residuals. So we don't want to see a form, and by form I mean a mathematical pattern, like a curve or a line or something like that. We don't want to see that in the residual. We want to see a nice random scatter of points. Okay, so another value that helps us determine if the linear model is a good fit for the data is the idea of the standard deviation of the residuals. Now, the standard deviation of the residuals is calculated in much the same way it's calculated for the standard deviation of the mean for univariate data. There's a big, huge formula, and it calculates all of the differences between the actual values and the line of best fit, and it shows me a typical distance that those residuals are from your predicted values. So in other words, shows me a typical distance between my actual values and my predicted values, because remember, the difference of those is your residual. Another value that helps us understand our linear regression a little better is the coefficient of determination, or R squared. It measures the percent of reduction in the sum. So in other words, it tells us about variability in the response based on the relationship between the response and the explanatory variable. A lot of the stuff I'm talking about will make more sense when I go to an example. All right, so okay, I think I'm going to end this video right here, and I'll make you another video for the rest of this. It's getting kind of long.